Wasabi, you guys. Welcome to Integration Bee Training for Advanced. This is part 14.1. In this section, we're going to learn how to do the Lobachevsky trick. So what on earth is the Lobachevsky trick? So, we know this is true if you remember your intermediate training on Dirichlet integrals. We had something like this. It was like from 0 to infinity. Sine of x over x dx. This is equal to pi over 2. It is also true for the squared version as well. For sine square of x over x squared dx also equals to pi over 2. Okay? So we learned that, these Dirichlet integrals, they both equal to pi over 2. Okay? So in Lobachevsky, whenever you have from 0 to infinity, you have sine of x over x, and there's a particular function, just a specific function that satisfies a certain condition, then according to Lobachevsky, the theorem states that this integral will equal from 0 to pi over 2 f of x dx. Okay? Now, you're probably thinking, so if this is not just any function, right? If this is a function that has to certify something, or that has to satisfy a certain condition, what is it? So there are three things that you must satisfy. Three things, actually. The first one is a little tricky. So, conditions. Okay. First off, is that the function must be Riemann integrable. Now, you're probably asking, what on earth does that even mean? Riemann integrable. Okay. And it has to be Riemann integrable at the interval 0 to pi over 2. Okay. But what does this mean? So, it pretty much just means, well, to put it this way, like in general, it just means that whatever function you have, it just needs to be like integrable. That's it. Right. This function just needs to be integrable from 0 to pi over 2. It doesn't have to be exactly continuous. Right, from 0 to pi over 2. It could literally be like this, and this is still integrable. Why is this still integrable? Because it's Riemann integrable. And what it means for it to be Riemann integrable is that I can go like this. I can splice this, and I could still take the area under the curve. Right? I can still take the area under the curve. Whatever this is. Right. This is Riemann integrable. Okay? Because this portion here, right, when you take the sum, right, there's like a, this delta x thing, where you can still take the rectangle here at the discontinuity, the splice. So this is Riemann integrable. That's all it is. In general, it just means like make sure this function is integrable from 0 to pi over 2. That's all that is. And then, right, if it had like something like an asymptote, you might want to be like very careful, especially like opposite asymptotes like that won't work. So, okay, so it just needs to be integrable from 0 to pi over 2. Okay, I'm not going to go in too much in depth into that, but the second and third one, it's just periodicity. So second one is pi minus x still satisfies the function, so it's periodic. And not only that, the function must be even. Even functions. Okay, the function must be even. Okay? Then, this will satisfy the theorem, the Lobachevsky trick. Sine of x over x, f of x, then this will equal from 0 to pi over 2, simply f of x dx. Okay? Just keeping these conditions in mind, and then you can just use this Lobachevsky trick. Alright, let's go ahead and get into our examples. Okay, so we have this simple example here. From negative infinity to infinity, this function is an even function, so we can go ahead and simplify this. Okay, so with symmetry used, what else can we do? So it's an even function, so we satisfy condition 3. Okay, 3 is checked. How about we see that our function is the absolute value of sine of x? You know, first of all, is this integrable? Absolute value of sine of x dx? Well, it is a continuous function, so clearly this is integrable. So this is definitely Riemann integrable. Okay. Is it periodic for pi minus x? So sine pi minus x, we know that this is going to equal to sine of x. So of course, number 2 satisfies. And this means that we can definitely, this is allowed. We can definitely use Lobachevsky. So, cool. And from 0 to pi over 2, it's always going to be positive, so we could knock this out. No, this absolute value. So we have 2 negative cosine of x. So our answer would just simply be 2. Okay? Alright, let's go ahead and jump into another example. So let's not freak out, this looks disgusting. Okay, so how do we approach this integral? Let's see, I notice we do have 0 to infinity, I have sine of x over x, then I have some function here, 1 over 1 plus cosine square. Okay. This looks like a Lobachevsky integral. But is it really though? Is this really a Lobachevsky integral? So let's test it. So first off, is this Riemann integrable? Well, this is 1 over 1 plus cosine square. So this is clearly a continuous function. So, I mean, because it's continuous, it's definitely Riemann integrable. Again, it doesn't have to be continuous, but most commonly, a lot of Lobachevsky integrals are continuous. But yes, this is Riemann integrable. Okay, cool. So 1 satisfies. Is it periodic? Right. Well, cosine square pi minus x is equal to cosine square of x, right? Because the negatives get squared. So, yes, it is periodic. And then this is clearly an even function. So yes, it's an even function. And so now, cool, this really helps us with ease that this is just from 0 to pi over 2, 1 over 1 plus cosine square. And now we can just simply solve this. Right, secant square, then secant square plus 1, this, 2 plus tangent square. This is what, 2 plus u square, right? And should just be like pi over 2 root 2. And that should be our answer. Okay, so Lobachevsky, very helpful, especially with weird trig integrals with an x underneath. You know, Lobachevsky can be very helpful and get around some ugly integrals very quickly. Okay. Ooh, a little scary, right? But don't freak out. We do notice that we have sine of x over x, and then we have sine 4x, and then cosine 4x here plus sine 4x here. Okay. Does this satisfy Lobachevsky? We hope. We hope. So, first off, this is definitely Riemann integrable because this is a continuous function. Number 2 is periodic. Is this periodic? Well, yes. We know sine will not change, and I know cosine will not change because it's in a even exponent. Then this is even function. Clearly, yes, this is an even function. So, very quickly, we could just go and say, yes, this satisfies the Lobachevsky trick. And so now, we have sine 4x here. Well, we could just abbreviate. And we already know this integral. This is equal to pi over 4. This famous integral here. This just follows Queen's rule. Okay? Cool. So this answer is pi over 4. So you are given an integral like this on an integration bee. Will you spam Dirichlet integrals? Right? You probably would if you were an intermediate. You would probably, you know, oh, this looks like a Dirichlet. Okay, this is a Dirichlet integral. Then with these two terms, you would spam integration by parts, right? But there's a faster way. There is indeed a faster way. Right? If we instead, what if we format it into a Lobachevsky integral? So let's say sine of x. We know this is 1, so it's like a plus 1 here, right? But then we have sine 4 minus sine square. Wait a minute. This is 1 minus sine square squared. This is simply cosine 4x. Would you look at that? We know this is continuous, so because the continuous function, this is definitely Riemann integrable. We know that this is periodic, satisfies the f of pi minus x equals f of x, and it's an even function. So, right off the back, we could just simply go like this, right? Instead of spamming integration by parts and using Dirichlet integrals, we could just go ahead and finish this integral off with Wally's product. This is pi over 2, 1, 2, 3, 4. Yep. And so now our answer is simply 3 pi over 16. Look how fast that was, right? So if you can, try to, you know, pull out a Lobachevsky before doing a Dirichlet, see if there's something nice. Okay? So we have a very difficult, intimidating integral. So, what do we do here? Okay, so there's a sneaky move that you'll come across when it comes to Lobachevsky integrals. Right now, seeing this does not look like a Lobachevsky integral, right? And I don't blame you. Okay, it's a very sneaky move. So, first off, what we can do, we can actually do a very sneaky move. Right, I'm going to let this portion be f for now. Right, so we have f. So we currently have f over x, f of x over x. So this this whole thing, let this be f for now. Okay. What you can do is you can go like this. Sine of x, sine of x. Okay? Now, is this function even, first of all? Let me actually go ahead and write it all out. So now, first off, is this function even? Is this function even? So we can see, let's see, negative, that's going to be a negative coming out, but let's say negative here and a oh no, I'm sorry, negative here and a negative here. Yeah, this function seems to be even. Okay, so 3 satisfies. How about 2? Is it periodic? I don't think so. It's definitely continuous though. This is definitely continuous. To go back, right, our function is not periodic, and we can clearly check that. Quickly check that. It's not quite clear, but we can quickly check that, right? Sine of x plus pi over 4, right? This is, if we do the sine law, right, sine of x, we have sine of x and then cosine of pi over 4. Cosine of pi over 4, square root of 2, right? But it's a positive, so we have sine, and then plus, and then cosine of x times sine pi over 4, which is square root of 2. Okay, so this is what we have, right? 1 over square root of 2. Okay. But if we do pi minus x plus pi over 4, this is going to equal sine of 5 pi over 4 minus x. So now let's do the sine law again, right? Of course, we're going to have the square root of 2 at the bottom, right? But where's 5 pi over 4? It's here, right? So when we compute sine 5 pi over 4, it's going to be negative. Okay, so negative and then cosine, and then minus, and then cosine of this is also negative. Okay, so that cancels out this negative, and then sine of x. So we have sine minus cosine over root 2. This and this is not the same. Therefore, this function is not periodic. Okay? Immediately. So, then how on earth are we going to make it periodic? So we need to know, what does A need to be? So in general, I want to do a U substitution where I could just kind of sneak a constant in there that would help us make this function periodic. Okay, but how? How on earth are we going to do this? So we want this where pi minus x, a pi over 4, this equals, in general, this would give us like 4 pi of 4a plus 1 minus xa. Okay, so here, originally, we have, well, we're going to have like square root of 2 at the bottom, right? And sine of a of x, so we have sine plus sine times cosine of this, okay? And then plus cosine of a of x times pi over, sine pi over 4, okay? So we have that, okay? But here, from this, we have sine of this whole thingamajig. Okay. Sine of pi over 4. Is there a way for me? Oh, no, I can't. No. 4a plus 1 then. I'll just write it like that. Okay. And then cosine of this minus cosine of pi over 4, 4a plus 1 sine. Okay. I wouldn't put a root 2 yet because we don't know what this is. Okay. But we want it to look like this. Right. So we want this to be positive. Okay, so I want cosine to be a positive, because this is cosine of xa. Okay. And what we have here is cosine xa. Okay. So we want this to be a positive 1 over root 2. So pretty much that's what we want this to be. Okay. But how? And not only that, we want this, because we need a positive sign, this needs to be negative 1 over root 2. Okay. Cool. So that's what we want. Alright, so in that case, we want inverse sine of 1 over root 2 is pi over 4. Equal to pi over 4, 4a plus 1. Okay. Let's cancel it out. We can actually have multiple solutions. It could be pi over 4 or 3 pi over 4, right? But let's test this out though. So we have 1 cancels a 0. Okay, so a is equal to 0. No. So, okay, so that clearly doesn't work, right? Okay. Alright, so pi over 4, 3 pi over 4 though, does. So, let's see if we cancel that out. We get 3 equals to 4a plus 1. We end up with 2. 2 equals 4a divided by 4. So we get a equals to 1/2. And does it satisfy here? Right? A equals to 1/2. 2 plus 1 is 3. 3 pi over 4 does equal to negative 1 over root 2. Awesome. So a is equal to 1/2. So that's what we want. We want a to equal to 1/2. Then this whole thing becomes periodic. Cool. Okay. So that's what we want. So pretty much we want x over 2. Okay. But how do we do that? Simple. U substitution. So we are going to force x equal to u over 2. And now this function is periodic. Awesome. So what we have now is we have sine of u over u, sine of u, and we have sine of u over 2 plus pi over 4. And then on the other side, it's kind of symmetrical. So we know for a fact that the other side is also periodic. Okay? So now, well, you can quickly check it if you want. It's the same process. Okay. So now this is periodic, continuous, and even function. Cool! Great! This is now a Lobachevsky integral. So now this is from 0 to pi over 2. We can quickly, we have this. We can just simplify this actually. We don't have to rewrite it. Let's see. From between 0 to pi over 2, this should be x over 2. I'm going to change it back to x. Pi over 4. And then this here between 0 and pi over 2, this is going to be a negative. So that means that we are switching. This would be, so that means that negative, so this would come out negative, which cancels out this negative. Right, because the interval from 0 to pi over 2, at this interval, this is a negative. So absoluting this will cancel out the negative here. Okay? The absolute value of this is negative of its is equal to negative sign whatever, because from 0 to pi over 2, it's negative here. Okay? So that's why that negative comes out when we compute the absolute value. So be very careful. Be very, very careful. Then we have sine of x. Okay? And then by trig identities, this is now equal, when you combine this, we get square root of 2 sine of x over 2 over sine of x. This is simply cosine of x, so 2 sine x over 2 cosine x over 2. This cancels out. So now what we have, so pi over 2 secant of x over 2. Perfect! This converges. Thank goodness. So now this is simply 2 ln. We could honestly go like that. 2. So we have square root of 2 instead. So now this is simply secant. Let's see, if you plug in 0, that's going to be 1. ln of 1, so it's 0. So pi over 4, secant of pi over 4 is going to give me what? Square root of 2 plus 1. Yeah, that looks very ugly. So, in general, our answer is square root of 2 ln of square root of 2 plus 1, right? Secant secant pi over 4 plus tangent pi over 4. That's where that comes from. This is our answer. Okay, and this is a very difficult integral. It's a very, very difficult integral. You have this sneaky move, and then you have this sneaky move where you have to find a constant where you force it to be periodic. Okay? Alright. So that is it. Again, I hope that was helpful. So Lobachevsky, it's very, very, very helpful. Very sneaky, but also could be a little bit difficult to maneuver. If you're trying to force a Lobachevsky like what I just did here, that takes a lot of practice and comfortability. So, yeah, definitely replay this video and try it on your own. Okay? Alright, thank you so much for watching, and I'll see you guys in the next part. See ya.